Yes, we have successfully used weapons to learn about delta G naught of a reaction. So our victims are still in the salt ring, folks. Now we know that delta G naught predicts spontaneity and the magnitude of spontaneity. But we also stated earlier on that free energy can measure the useful work of a system along with its spontaneity. So we can calculate delta G for spontaneity of a system. Now let's talk about how free energy, or delta G, relates to work. Thermodynamics evolved after the steam engine's invention, shaping a new era of machinery. And during this time, scientists defined the connection between free energy change and the work performed by a system as maximum useful work and minimum useful work. Maximum useful work is for a spontaneous process, and this process has to happen at constant temperature and pressure. So a spontaneous reaction is going to have a delta G of the system that is less than 0. This means that the system will do work on the surroundings, or work is done by the system. And if work is done by the system, then the work value will be negative. We can write an expression for a spontaneous process and say that delta G is equal to the maximum work, or work max, okay? And this is simply an expression to show a measure of the maximum work that a spontaneous process can perform. However, scientists found that for any real machine, the actual work done is always going to be less than the maximum because some of the delta G is released as heat. And we're going to see this when we're looking at minimum work as well. We see delta G releases heat. But for a spontaneous process, we can simply sum it up and say when delta G is less than 0 or spontaneous, our work max is going to be negative, and this whole thing is going to verify that it's a spontaneous process. But our work max is not whatever value we get for work max. So say, for example, we get 100 value for our work max. Guess what? We will not be using all of that workful useful energy because the delta G is going to release some of it as heat energy. So say instead of 100, you might only be using maybe 40 or 50, depending on whatever system you're talking about. Now, minimum work is for a non-spontaneous process. Again, we're still going to be at constant temperature and pressure. Now, although there is no specific expression for work minimum, since of course we tend to focus on spontaneous or max work of a system, the same understanding still applies. A non-spontaneous reaction means that delta G of the system is going to be greater than 0. And so this will only occur if the surroundings do work on the system. And so if the surroundings are doing work on the system, our work value will be positive. And same thing applies. For any real machine, the actual work done on the system is always going to be more than the minimum because some of the added free energy is wasted as heat. So again, we see the opposite happening with minimum work. And of course, we can sum this up and say when delta G is greater than 0 or non-spontaneous, our work minimum is going to be positive, and this verifies a non-spontaneous process. But we know our work minimum value, say our work minimum value is 100 this time around, then our overall work minimum that we see will be higher than 100. So maybe it'll be 110 or 150 or 160, depending on the system you have. And of course, a reaction where your delta G of the system is equal to 0 is going to be at equilibrium. So there is no work for us to focus on because there's no longer any work happening, right? For insight, let's explore work in a battery. Now we'll learn about batteries in chapter 17. So when we get through those lectures after exam number 3, we will get more details. But for right now, we're just going to tell you that a battery is like a packaged spontaneous redox reaction that gives us useful electrical power. Essentially, it releases free energy as an electrical current for various devices. So of course, we're talking for flashlights, computers, motors, etc. But we also know that useful work will be released mainly as heat. In other words, devices like light bulbs or motors, for example, don't use all the battery's power for useful work. And so we can use this understanding to calculate, say, the efficiency of common devices. Now, efficiency is simply just how much work we can get from the energy we put in. And that value is going to vary a lot among, of course, different devices. Here is a table of efficiencies of some common devices. So, for example, if we're going to look at a light bulb, the efficiency is only 10%. That means 90% is released as heat, which is why light bulbs are so hot when you turn them off after use, right? Whereas if you're looking at an electrical generator, you're going to have a more efficient device, and so it's going to allow us to use way more useful energy, and then less is going to be converted to heat. As you can see, we're able to use 95% of the useful energy when using an electrical generator, and only 5% is going to be lost as heat energy. So this just verifies what we already know. In real processes, some energy is always lost as heat, and no device uses all the available energy for work. Oh no, the salt ring is broken, and Tammy and Michael are at risk. We need to shift our focus to another factor influencing reaction spontaneity, and that is temperature. That information will get us the weapon we need to fight back. Let's get it, folks.